What's up geeks, and welcome to the channel. Students and developers alike struggle with the concept of complexity in software, so in this video we aim to provide a comprehensive exploration of this topic. To do that, consider an array filled with n integers and a piece of logic that sums all the numbers of that array. Let's try to find the memory or space used by this block of code. In this example, n equals 10, so we reserve 10 slots in the memory for the array and one additional slot for the total integer used to store the sum we are calculating. But not all arrays in the world contain 10 elements only, hence a better representation of the space used would be in terms of n, or n plus 1 in this case. Plotting this function will result in the curve we see in front of us. Let's move on to the time taken by our code to calculate this sum. To do this, we went ahead and calculated the exact time it took to sum up the elements. Then we gradually added to this list more integers and calculated the corresponding time taken by each array. If we attempt to plot the curve represented by the values we have, we will obtain a linear curve that can be written as an plus b. What we did here is calculate the exact values needed in space and time by our program, but that is not how we do things while developing an application. You see, we don't actually care what the exact running time of our program is because a lot of variables may affect that value. For example, these same arrays and pieces of code, if executed by a slower computer than mine, may result in a curve similar to the purple one, or by a computer faster than mine may result in a curve similar to the green one. So, what we actually care about is the variation, how the time taken and space needed are increasing based on the number of inputs. You see, these three curves are different, but they do share a common property: all of them are linear. The things that change are the a and b variables in the function an plus b, but the linearity is preserved, and that information is what we are looking for. So what we do instead of writing a bunch of mathematical functions is we estimate the need of our program by stating the highest order of the function we just calculated. The highest order is also referred to as the worst case estimate of the space and time our code needs to execute a given block of code, also known as the big O notation. So our space complexity will be O of n, as n plus 1 has n to the power 1 as its highest order. Same goes for the time complexity, as an to the power 1 is the highest order in this equation. But why do we do that? Well, we consider that if n is to grow infinitely in its worst case, the smaller orders will be negligible before the higher order values, and it will be enough to represent them using the highest order, in this example n and an. Okay, let's take another example, and in this one we print all the pairs of integers between 1 and 5. Let's try to calculate the space and time complexities behind this logic. Concerning the space complexity, we don't have an array nor a variable to store a total value, so the space complexity does not depend on the number of pairs nor our input. If n equals 100 or 1000, we will still allocate the same amount of memory for this block of code, leading us to a big O in space complexity of O of 1. Why O of 1? Well, if we try to write the space function with respect to n, and because it doesn't depend on n, it will be written using n to the power 0, which is equal to 1. Hence our big O is O of n to the power 0, or O of 1. Now, concerning the time complexity, we went ahead and calculated the time taken by our code to run and plotted the graph of time versus n. As we can see, it is a quadratic curve and can be written as an squared plus bn plus c. The highest order we have in the function written here is an squared, leading to an O of an squared time complexity. So, to recap, a computer program relies on two different aspects of complexity, space and time. Space is both the memory needed by the code to store information at runtime, which was the sum or total value in our first example, as well as disk space needed by code for persistent storage, which was the array storing the integers. Time, on the other hand, is the amount of time needed to process a block of code, or in other terms, the number of operations the code must perform to achieve its goal. Now, since these values may vary on several inputs, like the machine we are using, we tend to consider the worst-case complexity written as a function of the size of the input and expressed as the big O notation. These two complexities are the measure of how resource requirements change as the size of the problem gets bigger. They both affect performance. You see, efficient code uses fewer resources along both axes. The code can also be more performant if it uses more of the resources it has plenty of rather than those it lacks in. We will encounter a lot of examples during our videos where we will need to sacrifice space in favor of time and vice versa, and that is commonly referred to as the time-space trade-off in coding. Okay, if we look back to our two examples and consider that both of them are present in the same code block or method within our application, what will the big O of our method be in this case? We just discussed during the video that the first block alone has a linear time complexity, and the second one alone has a quadratic time complexity. This means that the total time complexity can be denoted as O of n plus O of n squared. In such examples, we always pick the worst of the two cases, or the highest order of the two, the one that varies with respect to time faster, and of course it is O of n squared in this case. Now, in front of us are the most common and used functions when it comes to complexity and big O notation ordered with respect to time. As you can see, there are quite a few of them, and you may be thinking, when do we have a log n or an n log n time complexity? Well, let's take the example we previously had and suppose that we are multiplying the for loop increment by 2 instead of adding 1. Now, given n equals 25, the code we just discussed will result in the output we see. So, how do we calculate the complexity of the following logic? You see, based on the output, we know that this for loop ran 5 times exactly. We can count the number. So, the exact time complexity is equal to the number of iterations, which is 5, times the time needed to execute a single iteration represented by the constant c here. But the challenge is to write it with respect to n. To do that, let's take a step back to the number 5. Why 5 exactly? Well, the number that forced us to break out of the loop is 32, and we obtained this number by multiplying the initial 1 we started with by 2 on every iteration. So, to break out of the loop, we executed 1 times 2 times 2 5 times, and that's 2 to the power 5. To generalize this result, we can write it as 2 to the power k, meaning we had to do k iterations to break out of this loop given an integer n. But what is the worst case? What is the maximum value that 2 to the power k can reach? You see, 2 to the power k will keep growing until it reaches n, or until it is slightly bigger than n. So, you can say that approximately in its worst case, 2 to the power k will be equal to n, right? Having this formula, we can wrap both sides by log base 2. The power k can come to the side, and knowing that log base 2 of 2 is equal to 1, we deduce that k is equal to log base 2 of n. Since k denotes the number of iterations, we can verify this result in our example. The ceiling of log base 2 of 25 is equal to 5. The same applies to the numbers all the way to 31, and until we reach 32, our breaking number, which is exactly equal to 5. But now you may be asking, if k is equal to log of n, what would the complexity be? Well, we previously established that the time complexity for this example is 5 times the time needed to execute a single iteration, which is equivalent to k times a constant independent from n, which is also equivalent to log of n times c. And since the complexity denotes the highest order value in a function, our complexity here will be O of log n. As a final example, take the same loop and wrap it with another loop going from 1 to n. In this case, we'll have two for loops, one with an O of n time complexity and another with an O of log n time complexity. The resulting complexity of such a code snippet will be O of log n times O of n equals O of n times log n. And that's it for this video. I hope it was helpful. Thank you guys for watching, take care, and I will see you in the next one.